Wow, that took a long time. You won't know that, dear viewer, wherever you are sat. You won't know that it takes a very long time to start this broadcast sometimes. I have no idea why. Anyway, good morning, good afternoon, good evening to you, wherever you are, dear viewer. Joined this evening by Sean Anderson, Dr. A, I understand, or Professor Sean Anderson, the drone data race, and Richard Ruiterkamp. It's going to be something like that. And the next problem I'm going to have with Richard's name is, or problem with Richard's company name is saying his company name. How do you say your company name, Richard?
Ampix Power.
Ampix Power. And the legal department in the house in the form of Jonathan Ruprecht, who I falsely said came from New York earlier and got that utterly wrong. It's actually from somewhere else.
More south.
So somewhere better.
More
better.
South. I guess you probably need all sorts of mapping to find that place down south there, don't you, Jonathan?
Yeah, right. Exactly. Yeah, maybe.
Yeah, all sorts of mapping involved there. And no thing about maps. No, I won't mention maps. Whatever I do, I must not mention maps. Right. Let's start with Sean. Sean, I was very excited and interested to read and see and then report about your drone data race, which to my mind was a very sensible thing, a clever idea, and a little bit different too. Let's get the right window up there. It's not that one, it's that one. There we are. The environmental data collection and need for speed, the first annual drone data race. Now, I think it's happened. How did it go and what was it all about?
It went really well. It was this past weekend. It was Earth Day. So we've been talking about doing this for a couple years, but we've just been so busy with our various programs here. We hadn't gotten it off the ground. This was the first toe in the water, relatively small effort, but it was a fantastic success. I'm really, really happy. My students really happy. Everybody was really happy with how it went. So the idea was we noticed that we've witnessed and we've been a part of drone racing starting to get bigger and bigger and bigger, which is cool. But one thing that has been sort of bothering me for a while is that our lab is constantly reached out to by folks that are trying to start a business using UAVs, and they really have the FAA thing down and the piloting thing down, and then they seem to think they're just suddenly going to start a business and make a gazillion $1 million. And generally speaking, not too much attention given to the actual deliverable. So what is this going to? What value added is going to be brought to the farmer, the whomever? And so I've been trying to push the fact that, yeah, that's great. I love the fact that you guys are flying safe. You got all the legal stuff and all the logistics stuff down, but what are you going to do for your consumer? And everybody seems to fall, or it's very common for people to fall down on that side of things. So been looking for a while for a way to bring people's fun with going fast and doing all that gearhead type stuff with something a little bit more, and also to perhaps reach out to more of the general public to show them the value of this new technology. And so we hit upon a data race, a race, but instead of just a race, have some element of data collection involved in that. And so the thing that we hit on, my lab does a lot with oil spills and managing oil releases accidentally in the coastal zone especially. And so the idea was, hey, what if we just had people run out and see if they could map a fake oil spill and come back? And so, for example, the fastest time, we had a course that was about 1.3 kilometers. At one point in that race, we'll have the videos up in a day or so. One point up in that race, we have a little mock oil spill, oil barrels, faux oil on the ground, etc. And the top time was 1 minute and 26 seconds from our racing drones. That got out there, correctly counted the number of barrels and returned. The idea was once they came back, they had to report the correct number of barrels of 2 different types, and if they were wrong, they got penalized in terms of their time. So it was awesome to see a little teeny, right? Several $100 racing quad. It can get out a mile or so away from you and back within 2 minutes and correctly tell us what's going on. I think the public can really get a handle of the value of that type of thing: search and rescue, environmental assessment, in a natural hazard type of situation. So it worked really, really well. So we had 2 races. We had one was we just run out and do that race, come back quickly. The second component was take a little bit more time and go out and see if you can actually image the spill. And we had great support and sponsorship from Pix4D, so we actually had Pix4D on computers here people could use. The prizes include Pix4D's licenses, and the idea there was to just use one of the photo stitching software options. People didn't have to use Pix4D, they could use whatever, to do some elegant presentation of the data, how much oil was here, how many barrels, etc. And we have huge plans for the coming year. This is going to be an annual event to add more and more onto it. And with the success that we've seen just from the folks that came to this and the inquiries we're getting, people wanting to fly down from from other parts of the state and other parts of the country. And I was like, whoa, this is our first one. Let's wait a second here. But I think we can really do some fun stuff that both sparks the interest of drone enthusiasts and racers in general, but also of the general public. So that was the overall goal.
So what was so it was mostly small FPV racer class machines, or was it the Phantom class of machine as well that was being used?
Everything. So this first one, we didn't know if we were going to get one person showing up or 100 people showing up, whatever. So we initially were going to have different classes. We just made it open. So we had everything from the FPV racers to Phantom 3s, Phantom 4s, some Inspires. We had some fixed wing, actually some really quick, nimble fixed wings. So we had virtually everything out there. Yeah, everything in between.
No, it's great. It's a really, really good use case and idea, and that's why I fell in love with the idea immediately and thought you were onto a great thing. So fair play to you and well done. And it's going to be interesting to see where this takes you, really, because obviously, is it a use case that the guys from Pix4D have considered much, oil spill mapping and things like that? Is it in their heads, or is it something they're going to have to refine for the competition?
They definitely thought about a disaster response or quick responder, like CSI type things. You want to get out and map an accident site or location, but not super focused on the oil spill per se. We actually have some programs in the state of California where we're trying to do more of this, but in general, not so much. But I mean, the cases are. I mean, let's talk. 2 weeks ago, I get a phone call from a reporter in New York City who sees what they think is an oil spill going on a piece of private property, and so they start asking me questions about all this and that, and I said, well, I don't know. It possibly could be this or that. I said, I really need to see some pictures. So they got just off-the-shelf Phantom and flew it straight up on the street level. They weren't spying. They were staying in the public sector, and they looked into the water in the area. And sure enough, I could tell with the booms, et cetera, so we could characterize that there was indeed a spill going on. And then surprise, surprise, when they asked the owner of the land, oh yeah, we spilled 26,000 gallons of oil there. So even with these simple camera, just regular visual spectrum cameras, these can be really useful in terms of hazard mitigation. So there's that level going on, and then there's also I think the tremendous possibility of bringing value that people don't even understand could be there. We do a lot with characterizing our coastline around the world, but here in Southern California as well, and the amount of money and time and effort we save, and the tremendous amount of additional value is crazy. So Pix4D is one of the tools we use, for example, to fly 15, 20-minute flight along the coast and actually get a full 3D representation of the entirety of these cliffs. Last year, we're out at our research station in Santa Rosa Island, which is an island just off the coast here, and we're doing some work with our underwater robots, our ROVs, and look down, and there's a human jawbone. What the heck?
Oh.
And so we call this is on a national park, and so we call the ranger. And first, we said, take pictures. That's what I say, take pictures. And then the ranger comes up and says, delete your pictures. And so we deleted all our pictures. And it was such a fresh jawbone, we didn't know, did someone just pass away? Did it was a shipwreck, what have you? Long story short, it turned out it was a shumage. It was a Native American bone that was probably on the order of about 10,000 years old that had eroded out of the sea cliff behind us. 2 weeks later, about a mile or so away, a woolly mammoth tusk tumbled out of the cliff down into the intertidal. And so the way we've traditionally been looking at, for example, our coastlines is for people like me to go out with a transect tape and lay it out and make a very precise, up and down, two-dimensional line through this area and then get a sense of what the coast is like. And then you need to walk down the coast, 100 feet and do another one, and then do another. Hugely labor expensive, takes a long time. With our drones, we can fly these things, get some fantastic UAV imagery, throw it into a product like Pix4D, and generate this high dimension 3D. And we can actually, by returning that, we can come back in and go, hey, where did the erosion happen? Way more value to our public sector, so our agencies charged with managing cultural resources, natural resources, hazard management, and it completely is going to change how we think of cost effectiveness and how we think of collecting data from the coastal zone. And so that's but one, the reporters, just a couple small examples that I think the public really doesn't appreciate. We're in the midst of our 3rd annual drone poll, which hopefully everybody takes. One of the clear signals we've been seeing there is we asked the general public, are you in general supportive of people using small UAVs? Are you not supportive of that? Are you neutral? What have you? And the short answer is about twice as many people have negative views than have positive views. But that's not the real story. The real story is if you add up the people that are neutral about UAVs and the people that are undecided, that's about 2/3 of the public. And so what that tells me is that's the big opportunity. Not that people are rah-rah or hateful, but rather the vast majority of the public is still on the fence. They want to know, is this a positive thing? Is this a horrible thing? And so I think efforts like this drone data race and a lot of the other things that we read about in SUAS News and other publications, that can really help frame people's perceptions of it. Should we support this? Should we not support this? Should we promote drone restriction legislation? Should we not do that? And so I see this drone race as one small part in helping engage in a broader cultural dialogue with about this technology.
I think your enthusiasm is shining through. Some feedback from somewhere there. I'm not sure who that's coming from. So, with your grown-up head on, it strikes me this has all been something really that's just really excited you and fired you up. That's a little bit bigger than your job as a professor or Dr. A, as you're saying. It seems it really is something that's caught your imagination. Would that be a good characterization? I
think so. Yeah. I mean, I was at major research universities for a while. I was at a big famous research university in the San Francisco Bay Area before I left. As I actually was leaving academia, so I mostly do applied stuff. And we have fantastic universities in our country that do wonderful things. But I'm mostly interested in trying to solve problems and move forward. And so I wasn't sure if academia was necessarily the place, or at least a large research university was the place for me. And so I left to help start this university about 15 years ago. So we're a little teeny tiny baby university. There's only about 6,000 undergraduates. But we serve a really different population than I typically have taught or worked with in my previous institutions. Our students here are almost all first-generation college goers. We skew heavily female. We have a lot of veterans. We have older folks. So we're the so-called underrepresented folks in the sciences. And what I've found is that drones are one of several technologies. A key technology that I can use to go to, say, a Hispanic kid who his parents are farm workers, and he doesn't think of himself as being part of the technology world or the technical economy. And I can say, yeah, come on in, dude, play with this. And so if I spin my computer around, you guys can see this is our lab. We have a bunch of 3D printers over there. There's a bunch of underwater robots, all this kind of stuff. All this is available to anybody around campus. So my students are here, but we have English majors in here, we have sociology majors in here, and they're just interested in the technology. So drones are like a gateway drug to get these guys into more technical disciplines. And typically my students, when they graduate, they go to work for the National Park Service, they work for agencies, environmental divisions of companies, et cetera. But increasingly, my students are now going to San Francisco, and they're going to San Diego, and they're working in the robotics industry. And one of the things that the industry folks tell us that they really like is the fact that our students get huge experience in all these things. So a traditional research lab, they're fantastic at making their propellers, and it's awesome. I love those folks. They do a fantastic job, but they really focus all their energy on the propellers. We're technology agnostic. We just want to get the data. We want to solve the problem. We want to answer the question for the municipality, for the company, whoever it is. And so we jump around on platforms as needed. We use commercial products. We use products that we build ourselves. We use a lot of open source stuff. And it's very much just sort of peer-to-peer learning with students. And so when they graduate, they've worked on 4, 5, 6 projects, and it's we were training the kind of employees that we hear that industry really, really wants. And so it's exciting to be a part of this and helping to put folks into the workforce, as well as helping to help push a technology, but push it responsibly, as opposed to the way we sometimes do with technologies. And I have many, many arrows in my back for the 6 years or 7 years we've been doing this, where certain risk management people didn't understand why we should be doing this kind of stuff. And so we fought the good fight, and we've won, but it has been a challenge. And if you didn't have a lot of energy like I do, obnoxious person that I am, I would have stopped long ago, I think.
Yeah, well, nothing comes easy in life, does it? And it always takes hard work. You know, you're the swan on top and paddling like Billy O down the bottom. So that I'm already looking forward to next year's event. I can tell it from your enthusiasm, it's going to be bigger and better. And I think it's a good time to bring Richard in now, because if you're dealing with oil spills, Richard's also in a sort of an oil mitigation industry. He wants to get rid of the oil-fired industry and be generating power using very complex or clever kites. Is that a good generalization, Richard? Is it just a kite? It's just a fancy kite you make, isn't it?
Well, yeah, it depends a bit on your definition of a fancy kite, of course. But no, it's a rigid wing high performance glider. We're flying that thing at 80 meters per second, driven by wind. And so it's a high performance complex kite, let's put it like that. But yeah, I mean, in its bare essence, it's an airfoil tethered to the ground, so that would make it a kite. Yeah. Yeah, so I don't know exactly where you want me to start the story, and I don't necessarily know how tech savvy the audience is. I mean,
oh, they're the finest. They're finest, and Bruce there in New Zealand he's got a rendering farm able to generate graphics at a moment's notice. Should anybody not understand anything, it'll be straight out with the pen. You know, I think people here are fairly technical, and I think I'm going to ask. Well, no, tell us a story, then I'll ask a question.
Yeah, okay. So I think that the easiest way for me to also not lose track of what I'm trying to say is by sharing my screen with you guys. So this is a very simplified rendering or moving JPEG, I think, or GIF of what the system looks like. Obviously, there's not much you can say of how it works from looking at this picture. So what I'll do is I'll quickly go through a few parts of our website to see if I can clarify the story a bit better. So I think that the best starting point is by looking at the academic rationale behind what we're doing. And so that's the most complete academic rationale was published in 1980 by a guy called Miles Lloyd in the Journal of Energy. And basically what he did was, if you look at figure 1 on my screen here, can you see my cursor as well, or is it invisible? Yeah. Okay, yeah. Okay, great. So if you look at this picture, it basically is a free body diagram of a kite where this Lloyd makes use of similar triangles between velocities and force factors. And the baseline story is that if you have a, let me see if I can quickly find something that would illustrate that now. No, not necessarily. Okay, let's switch back a bit. So the idea is that if you have a lifting body tethered to the ground, that there is a part of the decomposition of the tether tension that basically puts the whole system into equilibrium, which is we know this. If you look, if you watch a kid fly a kite on the beach, it's very obvious that this is a lift and drag generating device that is in at least in some form of stability with respect to the ground. It's not crashing down. So similarly, if you have any experience of flying a kite on the beach or watching kite surfers make these insane jumps that they do, it's obvious that there is energy stored into this system somewhere. So imagine that you have a kite attached to a mass on the ground. If you drag the mass around with a certain velocity, then simple physics tells us that this equates to a certain amount of power in watts. So the idea is actually a bit older than this paper, but the idea is that would it be possible to make an energy producing device out of a kite? And let's quickly jump to the rationale of doing so. If we look at the current generations of wind turbines, then basically this is quite an efficient machine to convert airflow into a torque and into an RPM, and thereby into an electrical power. However, once you start looking at the aerodynamics behind the performance of a wind turbine, one of the things you notice is that due to just velocity considerations, the outer 30% of a wind turbine blade generates roughly 70% of the power coming out of the machine. So if you now put on your economic glasses and you look at a conventional wind turbine, where are the costs located, then you would find that about 25% of the total cost of the system is buried underground by means of a foundation to compensate for the overturning moment that the rotor disc is exerting, or the wind is exerting on the rotor disc. Another 25% of the total cost is lost to the tower construction. And then we're not even talking about the infrastructure that you need to transport it and install it, and also install the foundations, etc., etc. So as an engineer, a conventional wind turbine is a stupid machine, because everything that does work doesn't cost that much, and everything that doesn't do any work costs a lot of money. So the basic idea is, what would happen if you would cut away all the stuff that costs money, and what are you left over with? So if I quickly jump back to I hope I can find this. Yeah, okay. So this is a very simple clip that's basically oh, let me kill the music. This is a very simple clip that expresses that idea. So the outer 30% of the blades are more efficient, the rest costs money. What would happen if you cut away everything that costs money? Well, what you're left over with is something that looks like this. It's a free-flying wing, or it's an airfoil at least. You need to stabilize it a bit by adding some fuselages and some tail surfaces and stuff like that. But in principle, you can track a somewhat similar pattern as the actual tip of a wind turbine blade. And so let's assume for a second here that we can prove in a few seconds that you can actually extract power from this system by means of a power transmission mechanism. Then what we have just generated is a similar system as a conventional wind turbine, but now without all the costly components. So that's basically the essence of this paper. Now there's two different things you can do. You can well, no, maybe let's step back 1 second. So if you look at figure 6, one of the more hidden features of flying tethered wings around is that there is a clear relationship between the aerodynamic performance of this system in terms of lift and drag, and the velocity that the kite can achieve with respect to the wind speed. So what I'm saying here is that by flying your kite in a crosswind motion, so basically the velocity vector of the system itself is almost perpendicular to the wind speed direction. And by doing so, a phenomenon happens that is also known from water skiing. If a water skier is dragged behind the boat by a tether, then if the velocity direction, if the velocity vector of the water skier is in the same direction as the boat speed, then obviously the velocity of the water skier is identical to the boat speed. However, if the water skier starts to break out of the velocity direction by having an angle with respect to it, then suddenly the water skier is traversing a longer distance in the same amount of time. And so it has to increase its speed to keep up with the boat. And this goes at the cost of additional tension in the tether that it's being dragged around with. So what we're doing is we're flying a tether, we're flying a wing on a tether, and we are steering it into a pattern or into a motion that is somewhat perpendicular to the wind direction. And the consequence of following this trajectory is that the velocity of the kite starts to become higher than the wind velocity. And ultimately, the the maximum velocity of this kite is a function of the lift over drag of the system times the wind speed. So that is interesting because by flying a perpendicular pattern, you can create a very large tension in this tether. And so once you have a controllable amount of tension, you can start thinking about a power conversion mechanism. So the more obvious one is, let's assume that you're flying this wing around, and let's stick a few wind turbine generators onto the wing. So now we have a wing that flies significantly faster than the wind speed. And by adding drag to this system by means of wind turbines on the wing, we now exert an additional drag force. And this drag force can be used to create work. And this work can be converted into electrical power and then transmitted down to the ground through the tether, for instance. Well, this is a system that's being developed by one of our competitors in the US. It's a company called Makani Power. They were acquired by Google X in 2013. So they have a slightly different development budget than we have. But having said so, money isn't all. So this is the way that one of the implementations of this system might work. The other implementation, which is actually what we are doing, is, I think, best explained by watching a slightly different video. I think there's a tail cam video in here somewhere. Yes, and it should be here. Yes, okay. This is an older video that we put on YouTube in 2012 already, so it's not that much of a novel thing, but it kind of expresses what we're doing quite good. So what you see here, if it's running, is one of our wings. It's a 5.5 meter span, 3 square meter wing, and as you can see, it's tethered. And so every now and again, you see the tether coming out of the. Here you see it. It's over here. Okay, so what happens now is that we're flying in a crosswind motion, so we're flying perpendicular to the wind speed, and by doing so, the velocity of the wing is increased to well above the wind speed. Like I mentioned in this video, I think we're flying at 50 meters per second, but ultimately we can fly up to 80 meters per second with this system, and by doing so, we are exerting a high tension on the tether. So this tether is wound on a cylindrical drum on the ground. And so by pulling on this tether, we are now expelling tether out of this reel into the air. So the tether becomes longer and longer. And now we have a torque acting on a rotary velocity, an RPM, in this drum. So after some time, so we are actually producing electrical power by multiplying torque times RPM. And at some point, we reach the phase where the tether length is its maximum length. And now we need to retract the system back to 0 again, to its initial tether length. If we would do so at the same velocity and the same RPMs, same tension, same RPM, we would obviously lose electrical energy by friction and conversion losses. But the fact is that we have a rigid wing aircraft that can actually make a diving motion. That's happening right now. So we are now flying straight and level back to the anchoring point of the system. And after a few seconds, while the tension in this tether is now almost 0 and we're reeling it back in again, we now again break out of the wind speed direction and we start producing power again. So this is basically the concept of what we are trying to achieve. In doing so, we and let's go quickly back to this paper again. So in doing so, we now create a system, and let's put some numbers to it. So if we would fly, I think it's what does he use again? A C5A, so not a small aircraft. In this paper, he immediately jumps to an aircraft of 576 square meter surface area. But if you would be able to fly such a big aircraft as if it was a kite, then such a system would be able to produce 6.7 megawatts of electrical power, while at the same time only using about 8% of the material with respect to a conventional wind turbine of the same size. So obviously there is an economic potential because we are reducing the amount of material used, while all else being equal, by about 92%. And this is, I think, the reason why we are trying to develop this technology. So if I quickly show you where we're at right now, we have been flying a 3 square meter wing fully autonomously. So, and what I mean by fully autonomously really means from start to finish without any human intervention already for a couple of years now. And let's face it, our flight mission is quite easy. Fly a pattern that makes money. That's basically the flight mission. Yeah, so that's quite easy. But it also means all the safety handling, all the off-nominal condition handling is all automated to a very high degree of autonomy right now. And having proven our concept for the last 8 years, we have started the design of a scaled-up version as of 2015, and that scaled-up version is now in the building state, so I can actually show you how it looks like. So this is a 12-meter span wing. It's 12 square meters service area, and it is the equivalent of 250 kilowatt of electrical power. So this is already quite serious in terms of power produced. So let's say that you can power about 250 households with this machine, while at the same time lowering costs and material use by a very significant fraction. Obviously, this material reduction comes at the cost of complexity. And this will only work economically if you can actually automate the hell out of it and be sure that you don't need any human intervention, because it would basically kill the economic proposition. So where do we stand with the realization of this system? So I can show you. And this is a part of our website where we try to basically inform the general public about the actual realization of this machine. So like I mentioned, the design has been frozen since December 2016, and we are now in the realization phase. So I can show you the status of the wing. And this also gives you an idea of the size that we're talking about. So this is the wingspan. These are the plugs that are required to create the molds. And so it will still take about like half a year before we can have the first products. But as you can see, it's a significant drone. And we are in the midst now of not only creating the structural components that are required, but also a big aspect is the sensors and control system. Obviously, if you're flying a heavy drone around like this, it's like a 350 kilogram drone, you do need to, keep track of the quality of the stuff that you're using. And so we're doing a lot of verification and acceptance testing on all different levels. So this is basically a GPS simulation that we did at ESA, the European Space Agency, where we do all kinds of system failures, constellation errors, pseudo range errors, all kinds of stuff to try to create our system which has the quality that's required to make this whole thing fly, literally. So yeah, I think this would cover a nice introduction.
Wow, my flab is aghast, and I think I'm going to throw it open to the floor for gentlemen. Do we have any further questions? I'm sure Bruce, you must have some questions.
I'm trying to get rid of the share. Oh, I'm back. Okay, sorry. Yeah,
you're back.
Yeah. This is so incredibly complex. One of the reasons wind turbines have been so successful is that they may be a waste of materials, they may be less efficient, but they're so damn simple that you put them up and they work. I can see so many failure modes with this proposition, and even some of the basic premises are sort of overstated. For example, this velocity thing, your aircraft's going to have a high velocity relative to the wind speed, but that's exactly what a propeller does. If you look at the tip velocity of a propeller in relation, or a turbine in relation to the wind that's hitting it, it's already much higher than the wind speed. So you're really creating propeller in the air, but you've got issues such as the winch generator. You've got a cable that's constantly being wound and unwound, the fatigue and so forth, and that's going to have to carry a current as well. It can't be something simple like Kevlar, because you've got to power that craft, the servos, the onboard electronics. So there must be a connection between the ground, electrical connection there to provide the energy. and you're talking about propellers on the wings, well, again, you're going to have a lot of little propellers, which are, by virtue of Reynolds numbers and so forth, far less efficient than a single large turbine. So I can see it's a great idea. The concept is brilliant, but I think it's going to be killed by the detail, the complexity. Even something like, you've obviously got different wind directions, and you've got this large wing, this large aircraft flailing around the sky. So you have to have an exclusion area all around there. So the actual ground area per watt generated is going to be massively greater than the ground area for a conventional turbine. And ground property is expensive. You have to buy that land or get a lease on that land. With a turbine, you only need the pedestal area to purchase or lease to generate your power. With this system, you have to generate a huge amount because you have to have the full extension of the tether and 360 degrees around in case something goes wrong and this thing collapses onto the ground. I can see a lot of problems that go beyond the science, that are practical, pragmatic issues that I don't know whether you've addressed. You could perhaps answer some of that and tell us what you've done to address those issues.
Yeah, of course. So obviously you are correct in a large amount of your observations, at least. However, there is it very much depends on the type of market that you're looking at. If these risks are actually allowable, or if you can mitigate them. So in Europe, for instance, especially where we come from, onshore deployment of wind turbines is it doesn't happen anymore, basically, due to the large congestion in Europe, especially in the Netherlands, Germany, the UK, Scotland, Denmark, and Germany. Everything is being pushed out into the North Sea. So in answer to part of the land use issues that I fully agree with, up to the point where you have actually significant statistical data to show that your realized safety case is on par with general aviation, this will be a no-go area. I fully agree in that aspect. Having said so, we have actually signed a first commercial deal with an energy company in Europe called E.ON that almost exclusively looks at offshore use cases for wind turbine technologies. In that sense, the infrastructural costs of installation of offshore wind turbines is quite staggeringly more than the cost of installation onshore. So this in part answers your question, not all of them. I do appreciate that. Yes, second aspect is yes, indeed. Before you can safely and reliably show that you are actually on par with the kind of ease of use of a wind turbine, you have some explaining to do. I have actually found, I don't know if you're familiar with the fact that in most wind turbines there are also control systems, and this is what happens if a control system fails in a wind turbine. So it's not completely on par with the fact that the wind turbine is a simple machine that has no failure modes that are just as detrimental. The other aspect is that in terms of the efficiency, the aerodynamic efficiency of the rotor disc itself, you're totally correct. So the tip speed ratio of a conventional modern wind turbine is in the order of 7, something like that. However, the use of the material is not as efficient over the blade length. So yes, the tip speed is actually quite efficient, but the rest of the structure is unevenly loaded. So what we are trying to do is we swap this lowering of efficiency in terms of rotor disc coverage by sweeping a much larger area. So all in all, the economics of this thing, of this technology, is a balance between material reduction and, on the other hand, the success of automation and risk mitigation. That's totally correct. It's not an accident that we have been working on this system for about 8 years now, whereas it has been working since 2008 or 9. So the rest of the time went into all the different risk mitigation aspects. Being able to operate such a system for a prolonged amount of time in an autonomous mode without any human intervention is the real challenge of this technology. I fully agree with that. On the other hand, if you look at the developed technologies, especially control technologies in conventional CS25 type of aircraft, it can be done, but it requires a significant amount of rigor in your design and in your control algorithm development, which is coming from process and from the organizational aspects more than there are hard limitations in the technology readiness or in the available technology in the world. So yes, obviously this is not a done deal at all. However, the economic potential of this technology is still sufficient that serious utilities like E.ON are in this early stage already investing time and money in doing a due diligence type of effort to see where this might go to. Mind you, I think that one of the more unique selling points of this technology are coming from a different use case from conventional wind turbines. If you look at the general distribution of wind energy over the world, what you see is that for most countries outside of Europe, the largest amount of installations are onshore. Like I mentioned, in Europe, this is the inverse picture. One of the reasons why that is the case is that the North Sea and the Baltic Sea are quite shallow. They're more like lake depths than they're actually seas. The water depth is 30 meters, 40 meters, something like that. However, if you look at the installation potential for offshore worldwide, then what you see is that the water depth is limiting the amount of offshore installations. And I don't know where you're located, where you're based, but the primary reason why onshore wind in Europe is not is on the losing end of the stick, let's say, is not necessarily due to the cost of land or anything like that. It's primarily due to public opinion. People just don't want to see them any longer, and there's a push in society to move all these installations away to offshore sites. So in deep water offshore wind installations, you are facing different challenges altogether. It's the overturning moment of the tower structure itself that drives the cost of deep water offshore installations. And this is actually where our first customer sees the bigger deployment potential of this technology. So not necessarily on land and not even in existing installation sites in shallow water, but it's ultimately the unique selling point of these kind of systems would be in deep water offshore installations. I hope that I'm answering some of your questions there, but
yeah. Another question, what is the operational range in terms of wind velocities of the system? Obviously, a turbine has a maximum and a minimum wind at which it can operate. How does your system compare to that? Because you've got a craft there. Obviously, if the wind speed is too low, it would stall and fall out of the sky. And if the wind speed is too high, it would be overstressed in terms of aerodynamics. So how does that compare with a conventional wind turbine?
We are operating at exactly the same wind range. So our cut-in speed at 100 meters altitude is in the order of 5 meters per second. The cut-out speed is a bit higher than a conventional wind turbine. So we're flying up to 28, 29 meters per second wind speeds.
Okay, so that basically is determined by the stall speed aircraft. How do you actually launch the craft? Because obviously it will have to come down for maintenance and so forth. So how do you actually get it off the ground into the air, and how do you get it from the air back onto the ground safely?
Yeah, so one of the more hidden features of this of the design of this drone is that we are not optimizing lift over drag. We are actually optimizing CL cubed divided by CD squared. So this is more similar to a conventional aircraft during launch and landing configuration with slats and flaps deployed. So that means that we are flying a 300 kilogram drone with a 3D CL max of 2.7. This ultimately converts down to a very low stall speed. So the 12-meter wing has a stall speed of in the order of 11, 12 meters per second. So that ultimately means that the acceleration over ground that you need is actually much, much, much lower than what you would expect from a similar sized aircraft. So we use that phenomena, or that principle, to do the acceleration over ground. So that's basically done by using part of the already installed infrastructure, like a winch and a tether, to do the acceleration. Then the second part is that you need a climb phase. Without going into too much details, because there are alternative ways without using propulsion at all, but that's a bit more complex to explain. But let's just assume that you have a conventional launch. So you're launching your aircraft into the wind direction. So after the accelerate over ground, it starts to it will have a, let's say, a 1.7 V stall when it exits the acceleration phase. Then there's a small propulsion system that takes over for a climb, and the climb phase basically stops at about 50 meters altitude. So the run time of the propulsion system is in the order of 6 or 7 seconds. After which the control system shuts down. You're maneuvering the aircraft in a downwind position, and from that position you do a normal conventional glider winch launch up to its operational altitude. And again, during landing, and oh, by the way, it's not the case that you stall the wing if there is no wind at all. There's actually a mode of operation whereby by inserting kinetic energy into the system through the tether. So basically you're pulling on the tether in certain phases of a flight pattern, and you're paying out tether in a different flight phase. You can actually have the aircraft stay aloft indefinitely if you want to, at the cost of a little bit of power, of course. So in terms of what the numbers there, you would have to spend in the order of 0.25% of the annual produced power to never land the system. But obviously, like you rightfully mentioned, you have to do maintenance, and it's not always economically viable to keep the system flying. So the landing is actually quite interesting. This is something that we've been investigating for quite a bit of time now. Let me see if I can quickly see if I can bring it up on the screen. So we are always tethered. Oh, sorry, I have to share the screen then. Yep. So we are always tethered to the ground. So what you see here is a passive system. It's basically a spring damper system attached to a bar, a horizontal bar, and the aircraft is only required to overfly the bar. And while doing so, it drags this horizontal roller pin, let's say, behind it, and it decelerates the aircraft in air. So we actually don't do landings. We overfly a landing system, and this has quite a significant error margin. So we've done a large number of tests that showed the use and the functioning of this passive system. And what it means is you can overfly a virtual window, which has about an 8-meter wide and 4-meter high type of dimensions. And as long as you fly into this virtual window at whatever speed, the aircraft is decelerated in air, and it basically stalls the aircraft. It drops out of the sky, and the landing gear is dimensioned to absorb that load. So that's how the launch and landing is performed. Having said so, of course, this is to a large extent the result of simulation and mock-up work on the one hand, and proving this with a system that is less sizable. So it's smaller, it's lighter. The real proof of the pudding, of course, is after demonstrating this at its relevant scale with this 12-meter wing structure. And again, I mean, I know that this sounds incredibly complex, and we are adding all these kind of systems with all these kind of failure modes, but we are nowhere near the phase where we are trimming down the number of systems. I really believe that it's possible to smartly combine a large number of these systems into something that still remains economic viability, just due to the sheer fact that you're cutting away so much of the material. And like I mentioned before, we have substantiated that vision, at least now with a significant first customer that is willing to take the risk in this early stage. ultimately, you have to try to do it at a significant scale. If in the end it proves to be less economic than what we have right now, then at least I think it has been worthwhile investigating the whole idea. Mind you, we are not the only ones in the world that are trying to develop such a system. I think at this point in time, there are like 50 or 60 companies. If there are hard stops, it's better to understand them in an early stage without everyone burning so much money as we have done so far. Maybe
I think it's interesting. You talk about the economies. Obviously, to be viable, this must produce electricity at a competitive rate to something like nuclear, conventional wind turbine, PVA, and all the other coal fire and sort of stuff. So how does it, what is the cost per watt hour? Have you actually sort of calculated that out and compared it to other options? Because if it's too expensive, people won't use it.
No, of course. I mean, come on. If it's too expensive, there's no reason to develop it. Based on single item quotes. So even if we just base everything on the component cost without economy of scale, our market introduction model, which will be a 2 megawatt version of this system, which is actually quite, it's not completely on par with the most modern wind turbines, but it's already getting in the same ballpark area, would have a market introduction levelized cost of energy in the order of 6 euro cents per kilowatt hour. If you compare that to onshore wind systems, that would be already on par in the first market introduction series. If you compare that for an offshore system, then we would cut in at around 8 cents per kilowatt hour for the first systems, whereas the capex costs, or well, it's not totally fair to compare the current installation costs due to financial engineering that's not accessible to us at this point in time. But the recent normal price point for offshore wind in Europe is in the order of 10 cents per kilowatt hour. And mind you, this is a market introduction value only. So if we extrapolate this a bit further in terms of how much can you leverage once you do economy of scale type of exercises, we can bring this down to on par with conventional coal-fired power plants. Having said so, a coal-fired power plant, of course, has a significantly higher amount of peak power output. But it's only fair to say that this is the same discrepancy between conventional wind turbine installations and conventional coal-fired power plants. Ultimately, there is still sufficient economics potential, even with a price point at market introduction, to further optimize this, to make it worthwhile investigating how low you can push this price. The biggest uncertainty is not necessarily the capex costs; it is the operational and maintenance costs. That's the more difficult part to model in this early stage.
I had a quick question about seasonality. So to me, one of the interesting potential applications of this is in places like here in Southern California, we have large periods where we have really peak wind, and then other times of the year when we have less consistent wind. 1, 2, we have a lot of concerns with migratory waterfowl and other critters. But those are, again, relatively discrete times of the year. It almost would seem that you could use a technology like this and maybe have two base installation points, and you could rotate the aircraft from in this area and fly it for those 3 months and then move it to that. Maybe that's too crazy an idea, but you would. One of the reasons we've not done installations to this point is because people are worried about some of those seasonal problems, and so the answer has been to disallow all wind productions altogether. So interesting.
So one of the more regulatory challenges, of course, is that you do need to have your permits and permissions in place. So that's a significant cost of the development of a project. To give you an example, in the Netherlands, to get the approvals for the installation of a wind turbine park roughly takes 7 years. We are not known for our fast moving regulatory, but So that means that developing a new technology almost takes as long as the installation permits. So from that point of view, I do think that this is maybe a bit off. But there is another switch point that's quite interesting. The wing surface area and the wing loading are relatively uncoupled or decoupled from the total load envelope. There is always a point where you have to introduce lower efficiencies in the system to not overstress the structures, like was previously mentioned by Bruce. So one of the means of doing so is trimming your angle of attack, but a second means of doing so is by reeling reeling out the tether at a faster rate, because by doing so the apparent wind that the kite sees drops down. So it's a combination of different factors that we use to lower the ultimate loads on this structure. So what that allows us to do is, for instance, to have two different configurations, a winter and a summer configuration, by changing the tether diameter and by changing the peak power of the generator on the ground. So we are looking into possibilities, but let's face it, it's sufficiently difficult to make it work at all. These are optimizations that we will take in a later stage. But by basically putting a less tensile strength tether, which has a smaller diameter, you can increase the efficiency at the cost of peak power. And so you would be able to switch between, let's say, a summer and a winter mode.
Wow, this is just, it's all extraordinary stuff. It's fantastic stuff and very exciting. And I can't. How many hours have you had just the strain on the servos must be quite incredible. Have you had them sat working on the bench for 1,000 man hours, 1,000,000 man hours now? I mean, what service intervals do you expect on this machine?
Yeah, so obviously most people are quite scared of aircraft maintenance, and that doesn't scale at all in terms of economics. This is absolutely true for a highly complex aircraft with, let's say, 1,000,000 parts. This is a significantly simpler machine. It's basically a hollow tube. It has a control system. This is all electronics. So the mean time between failure of the electronic components is pretty easy to model, as long as you take into account all kinds of stresses that it can experience. So like you rightfully mentioned, the biggest wearing parts, so the most maintenance prone parts, are the actuators. If you zoom in on where and how does an actuator motor fail, you find that it's not generally not the power electronics. It's not the MOSFETs that are doing the amplification. It's not the bearings inside the actual shaft assembly. It's not the rotor and the stator of the motor itself. It's the gears. And even there, if you zoom in within the gears, it's primarily the first stage of your gears that is wearing faster than all the other ones. So in our testing and verification, yes, obviously we are testing the hell out of those systems. And one of the things what we notice is that never trust the MTBFs on a data sheet. That's one thing. And the second thing is, once you start zooming in on what are the components that are actually wearing out, and what would that mean in terms of a replacement interval and a replacement strategy, then it's not that staggering. It's not that difficult. It's a feasible thing. It does mean, of course, that we are setting up deals with actuator manufacturers in terms of getting the first stage gear replacements cheaper than the whole thing itself. But this is something that's quite overseeable. In terms of maintenance intervals, we are talking about the first, so the gear stages. First gear stage needs to be replaced about every year or so. The total gear train has to be replaced every 5 years or so. The lower 200 meters of the tether needs to be replaced every year and a half, but this is a design input. The upper end of the tether, so the upper 800 meters of the tether, is replaced every 5 years. And if you take into account the cost of Dyneema or polyaramid or whatever the fiber of choice is, then you're looking about a replacement cost of roughly 10,000 euros a year. over a 20-year lifetime, that still is significant, but it doesn't compare at all to the cost of a tower structure that it fundamentally replaces. So also there we are looking at all kinds of replacement models and then servicing models. It's not killing economics at this point in time, and we do substantiate that with all kinds of testing and verification.
And just so I think I have it correctly in my head, once you've launched the thing, other than the service intervals, you'll try and use extra power to keep the thing in the air. You won't land it unless it really has to.
Yep.
So the wind drops. You're not going to land it. You're going to keep it in the air.
So on average, we have continuous flights of 3 days in a stretch. That's roughly by looking at statistical weather data of wind speeds distributions at the sites that we are trying to develop the system for. And so for a class 2 or a class 1 wind site, you get a certain wind distribution over the year. And if you look at the cut in and cut out speeds, on average, we would be flying continuously for 3 days in a stretch, and then you would be landing the system for about a day and a half until the next launch again. So that's roughly the type of intervals that we're talking about. The selection to either land or to keep flying is based on wind prediction data. So how many hours of non-economic operation are predicted, and based on those kind of inputs, we make decisions like landing and launching and scheduled maintenance and that kind of stuff.
Wow. And my last question for it, and we'd better move on. That landing platform that you had, does that rotate? Does that whole
Yep.
thing swivel?
Yeah.
Yeah. Okay. Yeah. So it's going to be an interwind situation for that landing then.
Yeah. Yeah.
As it were.
And this platform is, of course, it's an engineering step. This is not the actual shape and size and dimensions. This is taking into account all kinds of safety margins that we want to allow ourselves for this first iteration of such a system. We do already see that the length of this platform doesn't scale if we scale the system further. It will roughly remain the same dimensions, and it will become a bit smaller in diameter. Ultimately, it will be a bit more tapered, like a conventional runway type of thing. So also there's lots of optimizations that we're still looking into to further reduce costs and lower complexity, and thereby increase the robustness.
Wow. It's all wow stuff, and big thinking often leads to big results, doesn't it? So it has to happen that way. But it is just, if you start and think about it, it's just wow stuff. And now I'm going to move on to what's going to seem like fripperies, really. Fripperies from the world of unmanned aircraft this week. Mere nothings, mere bagatelles. Let's start with the. I think this week has been the only news really has been from the DJI camp, and the first thing I wanted to talk about was, or just mention really, not even really talk about, was the two things that are nice to have, as I described them, from DJI, and that was the tracking antenna and the new Posher controller. Bruce, have you got any thoughts on those things to start with?
Pretty old school. People in the hobby have been doing it for years. And but the thing I find interesting, the tracking antenna now, let me see, DJI is very, very pro safety. They even have this geo system that stops you flying in the wrong places. I don't know of any single country that allows you to fly beyond line of sight without special permits and exemptions. Yet they're providing you with gear that makes it easier to do that. So are they in favor of regulations, of following regulations, or against following regulations? They seems to be sort of a bit of both, isn't it?
No, I think you're misunderstanding them there. I think they're misunderstood by there, Bruce. I think what they're doing is they're allowing you to have supreme line of sight coverage. Never, no fault,
up to 7 kilometers.
Well, you need to get glasses like mine. These are really good glasses. and no, I think actually, did I see? I think I saw a figure of 1.8 kilometers on that thing for some reason. I'm not quite sure why, but yeah, tracking antenna and a controller with fancy bits. It's a nice to have, I think. And as you say, the established world's had that sort of thing for years, and the goggles as well. I've not even bothered putting on. Sadly, Loretta's not with us this evening because she's actually flown with those goggles. But yeah, I didn't even bother mentioning them today because goggles, you know, really. Goggles. And then memory. Okay, I'm not going to bother putting the pictures. We see the deal with Seagate as well. That looks like an interesting collaboration, and it speaks, I think, to DJI domination. We haven't heard anything from Jonathan. We don't even know if Jonathan's behind that picture anymore.
No, I'm here. I was just thinking primarily about that what we were just talking about, whether or not the DJI would actually sell that to specific countries, or they would be mindful of who they sell it to, because it'd be really bad if particular entities in certain Middle Eastern countries were to acquire that and start using it, and it would show up on LinkedIn.
Yes, this is the current place where a lot of those are showing up.
That's exactly what I thought of. I was like, uh-oh. I'm like, I wonder how long before that ends up on LinkedIn.
One more update, then you won't be able to use it.
Well, exactly. Well, I mean, I think everyone in the drone industry needs to start realizing that at some point here, we're going to start getting more and more regulated. Be careful who you sell to. Be careful who you train. Be careful who you talk to. Because knowledge has power, and if you put certain types of equipment, you piece together parts of the puzzle for certain people, then you have problems.
Well, I think you might be able to answer this. I think some parts of and Bruce actually knows more about it than anybody else probably, but knowledge and writing stuff down can become almost an ITAR item.
Oh, potentially. I mean, yeah, some of the technology is ITAR controlled, so you do have some problems there. Swarming technology and other things, so you need to be careful who has access. So I think it's just a point that everyone needs to be careful what they say around certain people.
But I think even just if you share an idea, that can be restricted in some ways as well. But it's a crazy world, and I didn't set it up, but did we see that the I forgot the name of them. The people that do the Dobby drone have bought out a drone display team in a box, 8 of them ready to go with 10 pre-programmed little maneuvers that they can do. So you keep mentioning swarming technology, Jonathan. You've also got worries about it. Well, you can buy it from China in a box now.
Well, that's nice. I mean, okay. Oh wow. I guess it'll be okay. The future's looking bright for doing drone defense, I guess.
Yes, for a small fee, I've been invited to 2 conferences today to tell me all about drone defense. It seems to be quite the thing of this week. Actually, it's absolutely what people are banging on about.
Drone defense is that's a problematic area. How do you counter these drones, right? So you have the jamming, the spoofing, the hacking. Are you going to just do type of actually destructive type of countermeasure? That would be an interesting show just to have in and of itself, because there's so many different ways to do it. And each of the ways that you can counter a drone has, there's repercussions. So if you use a shotgun shell, well, who's on the other side, right? If you use jamming, wow, now you just wiped out everyone's, Wi-Fi or whatever else in the whole entire area. Oh, you're going to jam GPS. Oh, I wonder how that's going to affect, certain types of aviation that might be flying on the GPS, and what happens if, in low visibility weather, when you have like an IFR certified GPS unit, you're going to whack out everything in the whole area. I mean, there's a lot of problems there with each of those areas, regulatory wise, liability wise. I mean, it becomes a nightmare.
Maybe I can add something to this discussion. I don't know if you guys are aware that the Dutch police has been using hawks and falcons to bring down drones to various levels of success and damage to the bird, I guess. But
I hate that for that very reason. I think so. The poor old birds, what they've done, majestic old birds, and knocked down the plastic. That's never right. It's never right. Never right.
Nope.
I'm never
But the
right.
downer to that is it's only you only have one bird for one drone. What if you have two drones coming in, right? That's the problem, right? So
The good
you
thing
have to
is,
have a
The swarm thing again.
no, but the good thing is that swarming in birds
Right.
is less frowned upon. So
well, that's actually a really good point. I mean, we can just get a flock of these things and just kind of unleash it. But I mean, it would be kind of cool if you're like the guy with like the falcon thing running around, right? You're kind of like, and then you get on a horse and it kind of be like out of a movie or something. Carry a sword, and you'd be like the drone hunter. Actually, forget drone law. I'm gonna do that. That sounds really cool. I'll play some like epic music. Dun-dun-dun, dun-dun-dun.
Indiana Jones is working on landing in whatever airport he can, so you know it works.
Yeah, you'll see me next time you go into an airport. You'll see me out in that grass. I'll just be like trotting along.
I do wonder if this is ITAR technology as well, by the way. But
Wow, yeah. Well, it's the training, isn't it? It's a crazy world we live in, and it's forced Bruce to wind it all the way back to having a .010 Cox motor and his 250-gram machine. You know, you're having a great deal of fun with that thing today, or whenever I saw that video, Bruce.
Yeah, it was good, pretty retro stuff. Yeah, a lot of fun. So things, what goes around comes around. But as I say, that's only valid in other countries. In New Zealand, it's still a regulated item.
Sure. Yes, it's true. It's true. Well, look, we've had an amazing chat this evening, and we've run well over time, so I better wind things up. And I'm not very good at this winding up bit, not very good at all in any of it really. But I must thank we've had cracking guests, Sean and Richard. Thank you very, very much for your inputs. It's very interesting. I'm going to take Jonathan's idea on board, and we'll invite some of these drone defense people on for a show, and we'll see what we can wheedle out of them. And I'll look forward to seeing whatever you're flying next. Oh, how's the pulse jet going, Bruce? That's got to be in the next episode. We're all waiting for that.
That's going to be as soon as the weather improves again, because it's going to pack up in a minute. Yeah, that'll be in the air, and I think this time we might just have it sussed.
Marvelous. All right, now I have to do those YouTubey things: subscribe, like, up, down, all those things that you're supposed to do. Don't forget to go and subscribe to Bruce's channel. We'll look forward to seeing the race next year, and I'm looking forward to my house being powered by a very fancy kite. So with that, gentlemen, thank you very much for your time. I bid you farewell. Bye-bye.
Thanks, you guys.
bye bye.
Bye.